to Biomedical Image Processing course. In this module, our objective is to see various pre-processing technique required for diabetic retinopathy. Author used 142 color retinal images obtained from a Canon CR645 non-mydriatic camera with 45-degree field of view for data acquisition. This consisted of 75 images for training and testing their classifier in the pixel level classification stage. The remaining 67 images were employed to investigate image-based diagnostic accuracy of our system. This image resolution was 760 by 570 at 24-bit red, green, blue, that is RGB color model. Using that, they have captured the image. One of the main obstacles for identification of retinal exudates in the wide variability in the color of the fundus from different patients, and this was the major constraints they have faced. This variation were strongly correlated to skin pigmentation and iris color. Thus, the color of exudates lesions in some region of an image may appear dimmer than the background color of other regions of the images. As a result, the exudates can wrongly be classified as the background of the image. This was major limitation of a current work performed by the researcher. In fact, without some type of color normalization, the large variation in the natural retinal pigmentation across the patient data set can hinder discrimination of the relatively small variation between the different lesions and their type. Thus, in the first step, we selected a retinal image as a reference and applied the described histogram specification technique to modify the values of each image in the data set such that its frequency histogram match the reference image distribution. So it will make normal distribution, uniform distribution among the image. The color normalization process was performed using histogram specification. In the second pre-processing step, the contrast between the exudates and the background is enhanced to facilitate later exudate identification, and this way the pre-processing steps will be a first step for the feature extraction. It will ultimately helps to get prominent age information of the image. The contrast is not sufficient due to the internal attributes of the lesions and decreasing color saturation, especially in the area around the fovea of the retina. Here we apply local contrast enhancement to distribute the value of pixel around the local mean of the value which has been considered for the purpose of pre-processing step. Our next topic is pixel level exudate recognition. Image segmentation plays a crucial role in most medical image analysis system by facilitating the description of anatomical structures and other region of interest of the images are prominently highlighted. Image segmentation plays a crucial role in most medical image analysis system, which will further help to get all the region of interest which we wanted to use for the purpose of grading and so on. segmentation technique vary widely depending on the specific application, image modality and other factors which are directly affected on the recognition process. Medical image segmentation is a challenging task due to the complexity of the images as well as the absence of models of the anatomical pathological structures that fully capture the all required possible information from the image. A segmentation method ideally locates those sets that corresponds to distinct anatomical or pathological region of the image which are our target for the process of grouping, clustering as well as classification and so on. If the constraint that region be connected is removed, the determining the set is called pixel classification and the set themselves are some type of group, cluster or classes which are required. Pixel classification is often a desirable objective in medical imaging, particularly when disconnected regions belonging to the same tissue class need to be identified for the processing. Here we report on the investigation made into the application of exudate identification at the pixel level which are based on the statistical classifier like any soft computing technique or fuzzy logic and so on. For each image pixel, a feature vector consisting of multispectral values of a pixel in a defined neighborhood and which was used as the feature representation of the image. Here multispectral, it means it has combination of visual spectral plus radio wave plus microwaves and so on. Multiple band data combined together to form an image, and this will help to get the images in such a way that few features which are invisible in one band may be visible in another band, and we can get all hidden information from the image with the help of multispectral analysis. An odd size square window was used centered on each underlying pixel in the data set which has been acquired during the grouping or during the collection of data. Then LUV color component, this color space was found the most appropriate space for our analysis of the pixel in the window were composed into the feature vector set. The selection of color space for image processing is application dependent. To select the most suitable space for our pixel based classification approach, we conducted a quantitative analysis and applied a metric to evaluate the performance of various color spaces which are used in this application. This metric estimated the class separability of our exudates and non-exudate pixel classes in different spaces and was measured using within class and between class scattered matrices which are formed from the images. After within class and between class matrices are measured, the following metric J which can be obtained as the product of TR multiplied by SB divided by SW, where SW is within class, SB is between class and so on. By following that method, we can able to calculate those values. A higher value of j indicates that the classes are more separated while the members within each class are very close to each other. By following this basic concept, we can able to form their groups. We have experimented with different color spaces and found that LUV color space is the most appropriate space for our retinal image analysis. Few of the results are compared and shown in this particular table number 5.1, which has comparative analysis of different color spaces. Thus, we choose their color space to carry out our pixel level classification task, and this is major task gives us good achievable result. There might be no constraint on the neighborhood window size n in theory, but it was assumed that most contextual information was presented in a small neighborhood of a small size of number of pixel. Here, to determine the optimal window size, we examine various pixel patch sizes. It may have like 1 by 1, 3 by 3, 5 by 5 and 7 by 7 also. To construct learning data sets of exudate and non-exudate, which include cotton wool spots, red lesion, blood vessel and some background pixel of the images. A consultant ophthalmologist manually segmented 75 pre-processed images and marked the exudate lesions in all the images which are being captured. An almost balanced learning data set of exudates and non-exudates was then established to eliminate any possible bias towards either of the two classes which we are going to form. This representative learning data set was comprised of 62,501 exudates and 63,046 non-exudates pixel on the images. To model the exudate and non-exudate probability density function, we choose one very commonly used classifier for every type of probability density estimation approach, that is non-parametric neural network, parametric GQ and semi-parametric GMM model for classification. Each classifier was trained and tested against our 4 pixel data set, which are of size 1 by 1, 3 by 3, 5 by 5 and 7 by 7. In KNN classification, number of neighbors, that is K, needs to be predefined. Here we experimented with different K values ranging from 1 to 7. K was chosen to be odd to avoid ties. To find the optimum value with the lowest misclassification error rate, and by considering that error rate we modify and have a different iteration. The best overall performance accomplished using KNN classifier. There few of the results are shown in comparative way in this table 5.2. The best overall pixel level classification performance is compared. As can be seen, this classifier achieved good generalization ability with a best overall performance of 90.26% against 5 by 5 pixel patch size dataset. In this case, the correct classification rate for the exudate and non-exudate classes was 88.92% and 91.60% respectively for the images. The Gaussian distribution is one of the most generally used density estimators. According to Bayes' theorem, the posterior probability is written by and calculated with the help of this expression, where probability of Ci over x will be calculated. The likelihood function, which having probability of x over Ci, was defined in terms of exudates and non-exudate class mean as well as covariance matrix. Probability of Ci was the prior probability denoting the probability that a pixel exudate or non-exudate which will occur in the entire set of pixel which we have been targeted. The posterior probability measured the probability of the pixel belonging to either the exudates or non-exudates class once we have observed the feature vector set of all the images of data set. Here the class detached to each feature vector x was selected based on the maximum posterior rule, and using this rule the further classification is done. Table 5.2 illustrates the overall performance achieved using the GQ classifier, and other classifier are compared with this GQ. Other are KNN and GMM classifier. The best obtained overall classification accuracy was 88.24% for a pixel size of 5 by 5 area patch size dataset comprising 89.14% and 87.34% correct classification rates for exudates and non-exudate type of lesions respectively. A disadvantage of parametric density estimation technique is their lack of flexibility when compared with non-parametric methods which are used by other researchers. Although single Gaussian density estimation models can be set up easily, they are restricted in their ability to efficiently estimate more complex distribution. GMM combine much of the flexibility of non-parametric methods with certain amount of the analytical advantages of parametric approaches which one may use. Basically, in a mixture model distribution, the data set is represented as linear combination of component density in the form of probability distribution of xy or probability distribution of xi, which is calculated by this formula. In this formula, k represents the number of components and each component is defined by wk and parameterized by mean vector and covariance matrix. The coefficients probability of wk is called the mixing parameters. We benefited from the theory behind these models and use a separate mixture of Gaussian to estimate the class densities, probability of x over ci of exudates as well as non-exudates by using this particular equation, where mu k and summation of k used to represent the mean and covariance of the kth component of the mixture density of class Ci. Ki denotes the number of components in class I and Ci refers to either the exudates or non-exudate classes of the feature set. Having estimated the likelihood function of these two classes, the posterior probabilities were obtained. The decision about the affiliation of each new feature vector X was then taken by applying the map rule on the feature set. We assume a full covariance matrix for each component since these types of matrices have highly flexibility in estimating the underlying distribution of the features. To determine the parameters of a GMM and fit a model to the data, the expectation maximization algorithm has utilized to measure the performance of the algorithm. This algorithm started with an initial guess for the parameters of the model and then iteratively modified these parameters to decrease an error function until a minimum error rate was achieved. The parameters were initialized using a k-means clustering algorithm. The k-means algorithm partitions the feature space into k number of clusters. To apply the k-means algorithm, number of clusters, that is k, or equivalently the number of components need to be known. Choosing too few components produces a model that can accurately model the distribution of the grayscale on the images. With an increasing number of components, the probability that the model fits the data set better will be increased, but the model also loses its capability to generalize that for other data set too. Here, the appropriate number of components was chosen by repeating the density model estimation and evaluating the minimum description length criteria of the feature sets. We obtained the optimum mixture model of each exudates and non-exudate pixel level data set separately by varying the number of components within a range of 1 to 20, and by following that it is found a good appropriate result. The optimum number of GMM components for exudate and non-exudate data set were found equal to 7 and 9 for a data set of size 1 by 1, 10 and 11 for 3 by 3 data set, 15 and 17 for the data set of size 5 by 5, whereas 19 and 23 for 7 by 7 data set respectively. It is equivalent that by increasing the pixel patch size, the model complexity was also raised and necessitated a higher number of components for effective density estimation. Here in table 5.2 summarizes the overall performance achieved with the help of GMM model. This model and other two models are compared to check their respective performance. Typically, the performance of a classifier improve up to a certain points as additional features when we added and then deteriorates the result. This can be seen in the same table 5.2 as performance continue to improve when patch size was increased up to 5. At this point, all classifiers achieved their best results. However, by increasing the pixel patch size, that is to 7, the accuracy decreased. In many situations, such as our application, it is valuable to obtain a 2D or 3-dimensional projection of the original multivariate data for the visual examinations. Here, principal component analysis was applied to the pixel dataset that achieved the highest classification accuracy, that is our 5 by 5 dataset size. The first two Exudates principal models contained 62.4% of the total variance, that is 49:7% plus 12:7%. Similarly, first two non-Exudates principal models represent 53.2% of the total variance, and this way we can able to get their current performance. The GMM classifier performed better than the other two classifiers which we have used in this particular case study, and provided the best result irrespective of the choice of pixel patch size. The best GM classification demonstrated an overall performance equal to 96.49% based on the 5 by 5 pixel level dataset. In this case, the correct classification rate for Exudates and non-Exudates were 96.15% and 96.83% respectively. Therefore, the GMM classifier with the 5 by 5 pixel level dataset was utilized to classify the pixel of new set of images. Now let us summarize. In this model, we have begin with various pre-processing operations on retinal images. Then these pre-processing will used for how to enhance the images so that we can get maximum feature set. Then we come to pixel level exudate recognition technique, and in detail we have touched to this exudate recognition topic. In next successive model, we will see various pixel level lesions detection techniques on retinopathy. Thank you very much.